Okay, off we go. So, last time we were talking about spherical coordinates. I'm not going to go through the definition of the spherical coordinates again. It takes a few minutes, but a couple of highlights to keep in mind. Theta is measured kind of around like that, sort of horizontally, you might say, around the z-axis. Phi has to wait for theta to be defined so that you know in which direction to be moving, sort of, you might say, vertically down from the positive part of the z-axis. Right? And then between the two of them, that defines a direction, and rho is the, air quotes, distance that you go in that direction, with, of course, the understanding that negative rho is perfectly allowable and just means that you go backwards. Okay. Alrighty. So this is where we ended last time, and we're going to pick up from there. What we're going to do is try to come up with formulas for how to convert from spherical to rectangular. In other words, if you know spherical coordinates, how do you infer the corresponding rectangular coordinates? And it's going to work off of this picture right here. Right, we're going to look at that triangle, and unfortunately, that right triangle, the way I have it drawn on the page, does not look like a right triangle, right? Because we're looking at it kind of at an angle, right? It's been sort of turned. We're looking at it from the side to some extent. So I like to redraw. Let's see here. Let me shrink just a little bit. I like to redraw so that I can look at it straight on. I find it a little bit more satisfying. You don't have to do that. That's just for your consideration. And with that in mind, we can now start doing a little bit of trig. Not that much, not that bad. Pretty easy observation that this distance, r, what we've called r in cylindrical coordinates, kind of polar coordinates, that distance r, you can see from this triangle right here, is just rho sine phi. Right, that's just a little bit of trig. Make sure you're good with that. Correspondingly, z, just a different side of that same right triangle, and a little bit of trig there, tells you z is rho cosine phi. Right, and again, just a little bit of trig, no big deal. It turns out that's basically all we need, because once you realize what r is, and once you realize we already knew that x is r cosine theta and y is r sine theta, right? We already knew that, right? Then that completes the list. Z, of course, we just got through solving for. Now we have formulas for x, y, and z in terms of rho, phi, and theta. So very important formulas. Make sure you know these. We'll be using these significantly for your consideration. Just a thought. I, in my life, have never memorized any of those formulas. I use them all the time. How do I use them if I haven't memorized them? And the answer is, I don't trust myself to remember. I do trust myself to be able to perform the trig as needed. Right? So notice it's not hard trig, right? It's an easy little picture, and trig is something presumably, hopefully, we're all quite strong with. And it's really easy to derive them as needed. So you might do both. You might go ahead and memorize the formulas and make sure that you know how to derive them. But I think knowing how to derive them is really important. Okay. Okie dokie. So let's do a couple of quick examples. I notice that if you have rho set equal to a constant, it's a sphere. Really, the easiest way to see this, I think, is to just remember that rho is, as long as c is positive, rho is the distance from the origin. And so this just very directly says distance from the origin is a constant, and that's basically the definition of a sphere. But if you prefer, you can plug into this identity, right? And that identity would then result in the familiar equation of a sphere that you may have seen in high school. Okay, and if not, that's the equation of a sphere. Okay, here's a fun one. Remember we talked about the non-uniqueness of polar coordinates. Because in some sense, there's kind of two different directions that you can use to get to a point in the plane. You can either go exactly the right direction, or you can go exactly the wrong direction by a negative r. Right? So take your pick. In some sense, two options. Well, there's two options for each of the spherical angles, and therefore there are four ways to write a point in spherical coordinates. And when I say four, there's actually infinitely many, but I'm going to say it's sort of a given that any time you add 2 pi to theta, you're just doing a full turn. It kind of doesn't really change the direction you're pointing. So obviously you can add 2 pi as many times as you want, and that's not what I'm talking about. So even ignoring that, there are 4 different ways to do a point. So let's talk about them a little bit. Here is a point in space. And there's a little bit of geometry that you can write down, geometry and resulting trig. Again, y'all are proficient with that, I assume. And so I'm going to presume that y'all can reason for yourself what these angles are like so. Notice I haven't labeled anything with spherical coordinates yet. Just talking about what those angles are sort of in, absolutes. Okay, so let's talk coordinates then. And we'll start off with the idea that we're going to use this value, pi over 3, for theta. Right? Remember, theta kind of defines a half plane hinged on the z-axis. With that defined, I can say, well, you know what? I could view phi as that angle, pi over 4. And then rho is, whatever it needs to be to get me to that point. And again, a little bit of geometry. So that's one way to go. That's a set of spherical coordinates for that point. Here's the thing. There are other ways to do it. And in fact, if I were to instead let phi be negative. Now keep in mind, positive values of phi bend down toward the theta half plane, so a negative value of phi would bend back away from the theta half plane. And if I do that far enough, that gets me pointing in a direction that is exactly the wrong direction, and then I can just go a negative 2 square root of 2 to get to the exact same point. Right, so for when theta is pi over 3, you have phi can be positive pi over 4, or it could be negative 3 pi over 4. And then just choose your rho to be positive or negative accordingly. Okay, so that's 2 possibilities. Now it turns out there's another 2 possibilities, and those are based on the other option for theta. Right, I could, instead of using this half plane, I could instead look at the half plane kind of on the wrong side, if you will. Right, go an extra half turn. And with that being the case, notice again we have a couple of different options. So one option for phi, and keep in mind the positive direction for phi is toward the theta half plane. That means it's that way now. That, when theta was pi over 3, that was a negative value of phi. Now, theta being 4 pi over 3, that same tilt, that same direction is now positive. Right? So, let's see here. So that noted, negative pi over 4 would guess going the correct direction. Right? Not positive pi over 4. And now it's negative pi over 4 because theta is pointing the other direction. And then, of course, you're going in the correct direction, so you'd have a positive value of rho. Or you could go in the positive phi direction. That phi would be positive 3 pi over 4. And that, again, gets you going in exactly the wrong direction. And then a negative 2 root 2 for rho gets you to the same point. So 4 different options, right? And it's very confusing. It's very geometrically challenging. By the way, do yourself the favor of practicing your three-dimensional drawing so that you can give yourself a very convenient, very helpful visual aid, such as what I've drawn here, right? There's just no getting around the fact that this course is intrinsically geometric. When things are intrinsically geometric, it's unavoidable that a good picture is helpful. And if a good picture is helpful, it's unavoidably beneficial to you to be able to draw them. Right? So I strongly encourage this. I know that some of you might see yourself as, I'm not good at drawing. There are things to know. Right? This is a skill to be learned and a craft to be practiced. Right? And so at the bare minimum, you can learn the skills, and I encourage you to spend some time honing those skills as well. Everything that I know about mathematical three-dimensional drawing, such as this kind of thing, I have put into some videos that are on my YouTube channel. They are in the playlist called Miscellaneous Topics. They're pretty bluntly titled Drawing 1 and Drawing 2. Right? And I strongly encourage you to take a look at those if you would like to know some tips and tricks for how to make better drawing and things to practice that will let you literally improve your drawing skills. Very useful. Yes?
Can you list the 4 theta and phi values?
I'm going to let y'all work out those details, and you can, of course, rewind the video and you can write them down from when I talk through them. But time's a factor, so I'm going to let y'all work on that. Okay. All righty. So let's see here. So here's a fun exercise. You can imagine the Earth being a sphere with its center at the origin, where the prime meridian is this right here. It's the, in the direction of the positive part of the x-axis. North pole being in the positive z-axis, south pole being on the negative z-axis, which I set up just for kind of convenience. So with things set up like that, it's not hard to persuade yourself that longitude and latitude closely relate to spherical coordinates. So you look at the picture and you realize that, which is theta, is also longitude east from the prime meridian, otherwise known as east longitude. So cool, right? We're halfway there already on understanding the spherical angles. Okay, so let's look now at north latitude. Well, north latitude is a little different. North latitude is measured like that. Wouldn't it be nice if it was convenient as latitude is phi, but of course it's not, right? Phi is measured downward from what you might call the North Pole here, right? So phi and north latitude are not the same. But you look at that picture and notice that the bigger latitude is, the smaller phi is, and vice versa. And so those two angles always add up to 90 degrees, aka pi over 2. And so north latitude relates to phi by that simple formula. So easy little conversion. Oh, and of course, every point on the surface of the Earth has the feature that its distance to the center of the Earth is pretty much constant. Of course, it's not exactly constant. There's ups and downs, right? There's mountains and there's valleys, right? There's also the bulge. I don't know if y'all are aware of this. Did y'all know that the Earth is actually kind of bulged flat, somewhat in the direction of toward a pancake, right? It's kind of like this, and it's because of the rotation. The rotation of the Earth creates, what we loosely call centrifugal force, right? And it pushes things outward, and it pancakes a little bit. So the distance to the the distance to the center of the Earth at sea level is greater at the equator than it is at the poles by quite a bit. I've forgotten the exact number. It's something like 30 miles. It's a ways, right? So related point, the point on the surface of the Earth that is farthest from the center of the Earth, you would think would be the top of the highest mountain, Highest above sea level? It is not. It's the top of some mountain in Ecuador. Because the Himalayas are a little bit further north, and they lose a lot as a result of that. So it's kind of a little fun fact. Yes?
Would longitude be up and down and latitude be left and right?
That's, you got it backwards. Yeah, longitude is measured this way, and latitude is measured north from the equator. Yeah. The confusing part is that longitude being measured sort of east and west results in what we call a line of longitude being a north-south line, right? And so it's easy to kind of get them backwards because of that. So, yeah, right. Okay. All right. Okay, so who cares? What does this do for us? Well, this allows us a really handy solution to a pretty natural question, which is that if I have 2 points on the surface of the Earth, maybe that's London and maybe that's Los Angeles, something like that. And if you want to know the distance, the relevant distance, of course, as the plane flies, right? Not as one could conceivably burrow under the surface of the Earth, right? Obviously, we're not doing that. We'd get into the mantle, right? The thing would melt. Right? So the straight line distance, completely irrelevant. Who cares? Right? But if you're flying a plane, you're following that curved path. And if you would like to know the distance, right, that you're going to fly on that curved path, how do you do that? Right? And a wonderful little argument is that for each of these points, I can use what we just discussed above to convert longitude and latitude to spherical coordinates. On the previous page, we have formulas for converting spherical coordinates to rectangular coordinates. So now that you know the rectangular coordinates for both of these points, oh, cool. Well, now you know them as rectangular vectors, and you can talk about dot product, right? And once you're talking about dot product, let's see here. The dot product of those two vectors is magnitude times the cosine of the angle. This is all easy computation so far, right? Both conversions are easy. Dot product is 3-function arithmetic. Radius of the Earth, look it up in a book, right? I mean, there's nothing hard so far, and we've got our hands on what that angle is. And of course, once you know that angle, the distance along the surface is just radius times that angle. So really clever little calculation. Spherical coordinates, very handy in that process. And, neat trick. Okay. All right. Okay, again, a nice little easy one. I'm going to let y'all read this mostly. This is something you do need to know how to do, but it's pretty straightforward. If you want to convert an equation from rectangular to spherical, notice all you really have to do after you kind of multiply out that x minus 1 quantity squared, all you got to do is just notice that x squared plus y squared plus z squared is rho squared, and recall that x is rho sine phi cosine theta, and it falls in your lap. So nice little process. No big deal. Make sure you're good with this. I think there's at least one homework exercise where we'll do something along these lines. So make sure you're good. Okay. All right. Okay. Here comes the uncomfortable bad news. You might say there are some disputes in notation as to what the names of the spherical coordinates should be. Different people, different groups, different organizations make different choices as to what we should call the spherical coordinates, and it's not for uniformly bad reasons. There are some good reasons. So, for example, what I have called rho, loosely speaking, the distance, the radial distance from the center of the origin, from the origin. That letter rho in physics is used to represent charge density. So the physicists, very reasonably, don't want to create that confusion, right? That'd be a real problem, especially because you use spherical coordinates quite a bit when you're talking about electricity and magnetism, where charge density comes up heavily, right? So they make different choices, and it'd be nice if one would just be the settled winner and you would never see any conflicting notation anywhere else. It seems just not to be the case, at least not yet. So you've got to be aware of stuff like this, right? So very common notation. I saw this kind of thing in my physics classes on the regular. Right? Not rarely. What we call rho, they call r. Despite the fact that we have previously used a different distance for r. Right? So that's confusing. It's very confusing. Now let me make the case for why that's a pretty reasonable choice. Don't forget, we have already agreed to use r vector to represent the vector coming from the origin. So they would make the case, and I don't have a counter argument, that, hey, come on, we're already using r vector for x, y, z. We're just talking about basically plus or minus. We're talking about the magnitude of that vector. Of course we're going to call it r. Right? And that's a reasonable case. And the other thing, and this is more frustrating to me because it seems so unnecessary, but in some circles, such as in physics classes I took back in college, what we call theta, they call phi, and what we call phi, they call theta. It's super frustrating. And again, not my fault. I didn't do it. Right? Don't blame the messenger. Right? There is no getting around the fact that you are going to see in your future conflicting choices of these notations. So here are some unavoidable realities. You cannot just make a choice for yourself, and I'm just always going to do it that way, and la 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 la. You can't make me do it, right? Not so. You're going to be taking classes from people using the other convention or a third convention, and it's not up to you. So you are going to see other choices, and you have to be able to deal with that. Good news. Our textbook uses the convention that I started with, and I think I've noticed that they use that pretty uniformly. So when you're looking at a homework exercise, a book exercise, they'll be, I believe, all using that same convention that we started with here in class. And so that'll, so just stick with that convention for those. If, hypothetically, maybe an additional homework problem, maybe an exam question, establishes by the statement of the question or whatever, some different convention, maybe such as the one that we just looked at below, you have to stick with it. This is not optional. You can't have an answer to a question and the answer and the question make different conventions on those things. It's unacceptable, completely confusing. We need to know unambiguously what you meant, and you can't just go around redefining things, right? So that, again, that's a non-starter. So you do have to stick with the convention of whatever exercise you're working or whatever exam question you're answering. So be careful about that, right? And you got to pay attention. You got to think it through. Lastly, if there is no established convention, right, so maybe there's some exam question where it's about something, some integral you're supposed to compute or whatever, and you decide that you want to use spherical coordinates. Good news, you get to use whichever convention you want to use as long as no convention was established in the statement of the question. The only asterisk is you have to be clear what convention you're using, right? So you've got to establish, either either draw a picture like that or write down the conversion formulas corresponding to the convention you're using. Or, and by the way, I think the following would be reasonable. You could say theta is the vertical angle. I think it's pretty clear what we mean by the vertical angle, right? If you say theta is the vertical angle and phi is the horizontal angle and r is the distance, and in the context of establishing your convention, I wouldn't quibble over using distance to describe that coordinate. That's fine, right? But you could just come out and say, vertical equals theta, horizontal equals phi, r equals distance, and now you've established your convention, and then do whatever, proceed as you like. Perfectly fine. Okay. All right. How we doing? Everybody all right? Okay. All right. Before I go on, I do want to make one observation, kind of in defense of this situation. Let's talk about the rectangular analog of this. Let's see. I'll just do it like down here. In a lot of books, this is always x and this is always y. True. But if you take an econ class, this is P and this is Q. Right? Now, you can't be thrown by this. Right? And there's a million other contexts, such as, in engineering, you're going to be looking at relationships between variables that don't happen to be called x and y, and that's fine, and that's something you could just adapt to, and you just have to, keep in mind, have an established choice of what choices you're making, and make it unambiguous, and then go about your business. Right? So not that weird, really, when you think about it in that context. So that's really all we're talking about, just for spherical instead. Okay. Alrighty, moving along. So there's this thing called standard basis vectors. Again, big deal in linear algebra. Y'all know the rectangular standard basis vectors. Again, these were figured heavily, I'm sure, in your Math219 classes. IJK is a common choice. If you know 100% for sure that you are and always will be in 3 dimensions. I like to point out that if you're not in 3 dimensions, this is a much better convention because it's easier to see how that generalizes. Right? If you're dealing with 7 variables, E1 through E7. Nice and simple. Okay. All right. Okay, so various cool things about them. One is this. They're the unit vectors that point in the direction of increasing a single coordinate of that coordinate system. Right? In other words, for example, if you look at E2, that's the direction in which x and z are held constant and y is increasing. Nice feature. Well, this property is something you can do in other coordinate systems. So, for example, if you are at a point right here, right, you can talk about, well, which direction would I go to hold theta constant and let r be increasing? And the answer is I would go that way. And a little bit of geometry will persuade you of that formula. And that's a nice exercise. Make sure you're comfortable with where that comes from. Let's see here. And then, of course, the other would be like so. That's the direction where r is at least instantaneously held constant and theta is increasing. Okay? And a little bit of exercise will result in this formula for E theta. Okay, so these are the polar standard basis vectors, and they're useful here and there, and so you've got to know what they are. Yes?
For U theta, would R change over time, or is it just
Well, yeah, so what we're talking about is instantaneous, right? So at that, if I were to go in the direction that I'm calling there E theta, if I were to put on the blinders and just start going in that direction, eventually R would increase. But that's just not what we're talking And here's the other awkward thing, and you'll notice very quickly from the formulas there. I can't say to the question you asked if you keep going in the E theta direction, because E theta changes as you move. Right? So E theta kind of curves around as you move in that direction. So that's another little awkward reality that we have to recognize. The rectangular standard basis vectors are constants. They're the same vector everywhere. The polar standard basis vectors are not constants. Okay, so something to think about, and an exercise to do for yourselves. I think this is healthy. Is to persuade yourself of the cylindrical. I mean, we already have the ER and the E theta, but the third cylindrical standard basis vector is like so, and the spherical standard basis vectors are like so. And I think it's a nice exercise to derive these formulas. Now, you'll notice that this is optional, right? You don't have to derive those formulas, but it's good geometric geometric weightlifting. Something that will make you geometrically stronger and more experienced. Okay. All right. So, as we just observed, they're not constants. Sorry. Right? But that's an unfortunate reality we have to deal with. They don't play nice linear combination games, right? So we've talked in the past about how rectangular standard basis vectors are really nice. Coordinates give you coefficients when you're using standard basis vectors. Not so for spherical or polar or cylindrical. So, again, sort of, bummer, bad news. Okay. Conveniently, they are orthogonal for all three of these coordinate systems we've talked about. That is kind of a happy little coincidence. It's not true for every coordinate system, but it is true for these coordinate systems, and that's cool. Okay. Alrighty. So, moving along. We're done with Chapter 1, by the way. How about that? Moving on to Chapter 2, there's some things that need to get established. Some definitions and some notations and some terminology. Yeah, it just kind of has to get done. It's tedious and it's perfectly readable. And so you'll notice that most of the next 2 pages, or is it all? Let's see here. Yeah, it looks like it's all of the next 2 pages I have labeled as students to read, right? So do make sure to read through all of this. It's little boring but important details. I am, as usual, going to hit some highlights, the things I think are particularly worth noting. So first of all, common misunderstanding as to what a function is. A lot of people think that a function is, some formula you write down. And that's just not true, right? Now that little misunderstanding you can kind of get away with in, high school algebra. Okay, I guess it's fine. But honestly, even when you get to single variable calculus, this misunderstanding is a problem. It's a problem that gets glossed over in most single variable calculus classes. We're not going to be able to deal with the level of problem that's going to be in this class. So we are going to have to be more careful. And a function is a trio. Specifically, it's a domain, a target, and a rule of assignment, which you're going to think of, and it's fine to think of that as, kind of the formula. Okay. So here's a nice example. We can talk about the function that I'm going to call the student ID function. And let's look at how we might define the student ID function. And let's compare these 2 candidates. And notice they have the same domain. F and G, these 2 different functions I'm calling F and G. I'm defining F and G from the exact same sets, namely the collection of all students. Let's say all students at Duke. Okay. I'm going to use the same rule of assignment. For any student at Duke, the way I compute the value of F and the value of G is What is that student's ID number? Right? Every student's got one. Okay. Well, I mean, all student ID numbers are integers. I'm pretty sure, right? I don't think anybody's got a fractional student ID. Those integers are also. Oh, I can't. I've already used blue. Sorry, hang on. Let me use this other. Use purple. Every student ID number is also a real number. So either one of these choices for the target is fine. Right? F, as written there, function, no problem. Perfectly good function. G, as I have it defined there, all good, no problem. Perfectly good function. Every point in the domain has an image that is a point in the target. That's all you need. Right? Perfectly fine. But these are therefore different functions. Right? So these being not the same means we have different targets. That means we have different trios, and that means that F and G are different. They are not the same function. They have different targets. I know that seems fussy. Right? You'll see in a minute why we care about this. Okay. All right, a little bit more terminology that's very readable. Do make sure to take the time. What I'm building up to here, and this is just one of the reasons that we need to be fussy about this kind of thing, is let's talk about what it would mean to invert a function. And so here I have an abstract function written where I have an abstract domain consisting of just 3 points. Right? That's not that practical, but very convenient for an abstract point. Target consists of just 3 points, and again, it's not that like that's going to happen that often, but we're just making a conceptual point here. And we have our rule of assignment, which is going to take every input and give me the corresponding output. And every input has an output. Okay. So this function is what we call invertible. And invertible just means that you can turn all of these arrows around backwards and have another perfectly well-defined function. And so in particular, that's the domain for my inverse function. And that's the target for my inverse function. And I claim that you need this perfect pairing. This, you'll read the discussion there yourself, but 1-to-1 and on-to are the words that we use there. But this perfect pairing, everybody's got a buddy kind of relationship, is necessary to be able to talk about the inverse function. And by the way, you can probably see where this is going. We use inverse functions all the time, right? There's the sine function, and then there's the inverse sine function. I like to call it arc sine. Right? Stuff like that. Square root is supposed to be the inverse of the square function. Right? So we need to be able to talk about inverse functions. Notice that if your function is like this, you can't even talk about the inverse of that function. There is no inverse of this function. What, pray tell, would the alleged inverse function do to that point? It's got an indecision problem. You can't send, in a function, you can't send something to two totally different places. Right? Functions can't be ambiguous like that. It's just not allowable. So that function's not invertible. And then in a different way, this function is not invertible. Because where would you send that? Sad little member of the would-be domain, right? What's the inverse function applied to that? I can't turn its arrow around. There is no arrow to turn around. Right? So again, we're out of luck on that one. So you can't have any of these kinds of problems. You have to have something that is importantly like this. You need the domain and the target to have this perfect pairing kind of relationship, and you can't even talk about that unless the domain and the target are part of what you defined when you define the function. So this is why we have to be fussy. So let's take a look at an example of this. And we'll look at this top example up here, but if you're bored by that, you're welcome to look at the bottom example. It's trig related. So there's our squaring function. Put any real number in. No reason immediately to restrict it being okay from any number coming out. Perfectly fine as a function. No problem. But it is not invertible. Right? If this were invertible, I would have to be able to tell you what is the inverse function applied to -4. And I can't because there is no other number whose square is -4. Real number. I also can't tell you what would be the inverse function of this as applied to 25. Because -5 and 5 both land on 25. Which one do I pick? It's not clear. Right? So this function is not invertible. There is no inverse function at all. So the way we resolve that matter is we just restrict the domain and the target appropriately. And notice here we're in business. Oh, whoops, I missed the thing here. Now we're in business because whatever non-negative real number you give me, there is exactly one non-negative square root. That function is invertible. That's what you might call the invertible square function. Okay. All right. And you got to set all this up, and you have to have your convention established before you go around talking about inverting stuff, because again, it doesn't make any sense otherwise. Okay. All right. Okay, good exercise to think through on your own that, again, sine theta has this problem that, sine theta defined in the usual way, real number in, real number out, is not invertible. It's not even close to invertible. It's even more wildly non-invertible than the square function. But if you restrict the domain and the target like so, if you allow only these values of theta and only those values of y, right, then in fact this is indeed invertible, and pictures below to make sense out of it. Okay. By the way, the inverse function is called arcsine. Okay. All right. Okay, the rest of this is all readable. Make sure to read through all this. Again, some important terminological conventions we have to standardize. Just read, make sure you retain on that. And likewise, another little bit of terminology, and then the fun little example of a multivariable vector-valued function. The weather. If you want to talk about the weather, you got to tell me where, how high above the ground. And are you talking about now or yesterday or 2 weeks from now, right? The weather is defined with, there's several inputs that we have to establish before we can even talk about the weather. And then, what do you get? How does one describe the weather at a location, altitude, and time? Well, we can talk about the temperature, the pressure, the wind speed, the humidity, etc. Right? So when you're talking about the weather, right, the most trivial of water cooler conversations, right? You are talking about a multivariable, vector-valued function, right? Arguably, you're talking about actually a pretty sophisticated mathematical object. Okay, and that's just the weather. So imagine, if you're, I know y'all are mostly engineers, and if you're building an engine, there's a bunch of different parameters, and gas, air, mixture ratio, and liters of displacement, and blah blah blah. Right, a bunch of stuff, much more complicated than that. Okay. All right. So moving along, see how we're doing on. Okay, we got 5 minutes. Yeah. So here's an awkwardness. Functions, really important thing. Arguably, that's what this course is about. right? And this course is about calculus. But calculus is stuff that you do to functions, right? So if you're going to do calculus to functions, it's nice to be able to talk about how to visualize those functions. Part of the reason being that if you can visualize the functions, then you can talk about visualizing the calculus. You know, what does the calculus look like geometrically? Well, it depends on how you're visualizing the function. So an easy example, y'all have heard this a million times in a Calc 1 class, you talk about the derivative, that's calculus, as being the slope of the tangent line. That's a geometric concept based on a picture you have drawn of the function. Very specific picture called a graph. Okay. All right, so let's talk about graphs. That's one way to visualize functions. And here we go. Now, what I've written down here is, little math formalism, kind of rigorous, fussy. If you really want to get precise about that, then there it is. You don't have to, but I think it's healthy. But the big idea here is that when you say the word graph, let me use a different color there. When you say the word graph of a function, what we're talking about is looking at all of the input values, all of the resulting output values, and the graph is what you get when you look at points that kind of slam those together. Right? You take all the coordinates, the input coordinates and the output coordinates, and you use that to make points that have multiple coordinates, the first few of which being input coordinates, the last few of which being output coordinates. So a little bit of a weird construction, but very familiar, I'm sure you'll agree. We look at, here's what a graph of a single variable function is. Here's our single variable function, right? And notice, all we're doing is we're taking the input value x, the output value y, we're smushing them together. Oh, I forgot to color the y there. We're smushing them together then to make points. That's points in 2 dimensions. Right? And if you do this for all the inputs and all the corresponding outputs, that will then trace out that curve. So that's the graph. The graph is, again, what you get by smashing together input and output coordinates. Does that look familiar to everybody? Everybody on board with that take? Okay. All right. Here's a different way to think about it. I like the following as well. Let me real quick talk about this function. Remember, a function is 3 things. There's the domain, there's the target, and there's the rule of assignment. There's the rule that tells me how to take an input and produce an output, typically a formula. Right? And notice, in that function, I've established the input and output spaces, the domain and the target. I've established that there's got to be some sort of a formula, but I have not given any sort of a name to what the output variables are. You can have a function like, f of x equals x squared, real numbers in, real numbers out. I haven't given a name to the output coordinate. You kind of have to give a name to the input coordinate to be able to talk about, what you're going to do with it, right? But I haven't given a name to the output coordinate. So I like to think of a graph as what results from when you take the formula for the function and you give a name to the output, right? So the act of naming the output is ultimately what creates the equation whose solutions are the graph curve in this case. So different way to think about it, just give a name to the outputs, or as we saw earlier, solving for one of the variables in terms of the other variable. Okay, so let's see a higher dimensional version of this. Okay, well, if I have a function that has 2 variables, if I put the inputs first and the output second, then notice now I get a bunch of points in 3 dimensions. And again, the inputs are kind of, if you will, kind of happening. This is a little sloppy, but very, very satisfying. It's like the inputs are in the horizontal plane, and then the output is in the vertical direction. The output is, you might say, upward. Okay, so if you do that for every possible input, right? If for let's see here, for every point in the plane you move upward by the amount specified by the function, for every point in the plane you do that, you get a bunch of points up here in space that make a surface. Does that make sense? Okay. So this is our first picture that we're drawing of a multivariable function. Notice we have multiple input variables, 2 input variables, and here is a kind of a picture of what that looks like. Right? This is the graph of that multivariable function. Okay, now, familiar idea, we like it, but here's the problem. Oh, God. Okay, real quick. If you were to have as many as 3 input variables, notice that means you would have a total of 4 total variables, 3 in, 1 out. Note that makes a 4-dimensional picture. You can't even dream about visualizing or drawing such a thing. And so the graph construction is useless in that context. If you have 3 input variables, the graph is basically an inaccessible concept. So we run out of business pretty quickly there. We're going to need other tools to be able to talk about such functions. We'll pick up there next week. Y'all have a great weekend. See you later.